Hello and welcome back to Calculus 1. This is section 3.7, the chain rule. All right, hands down, this is going to be the most important technique to take derivatives. Almost every single derivative you take from this point on across all of the calculus differential equations will be this one, the chain rule. How often do you take derivative of sine x? Almost never. How often do you take derivative of omega t? Almost all the time. So the chain rule is going to be the derivative of function composition. And this is, as I said, the most frequent occurring derivative in the galaxy. Okay? So chain rule is the derivative of function composition. Now, we have to review first function composition from pre-calculus. It was covered in chapter 1. Those of you who took PreCalc 1 with me, you know that I said this is something that will never go away, and it's going to play a key role, central role in calculus. So here it is. If you have function f of x just as a square root of x, we can think of that as a vanilla function, right? You know how to graph that, we're good to go. Nothing special going on. But then you can have f of x equals to square root of sine of x. So now you have a function sine x plugged into the function square root of x. Obviously, graph for this is going to be much trickier. We have to think hard about domain, range, intercepts, and all other things. To make this much worse, we can chain as many functions as we want to or need to. So we can chain 10 functions, one into another, plug into one into another, and make a function composition. The notation for, so in this case, we would say that f of x, sorry, I called it f of x. So g of x is root x, and h of x is sine x, and then f of x is g composed with h, also denoted as g of h, depending on which way you remember it. So this circle notation is it's not a multiplication, it's a circle, but it's operation. So that's not goch, okay? It is g composed with h. All right, that circle is not O. It's actually multiplication symbol, which is actually a circle. So what we have here is one function gets plugged into another function. And guys, this is everywhere. You will take care of sine x squared. You will take care of e to the x squared. You will take care of all of this, like ln of x squared plus 3, right? These functions are far more frequent with calculations and engineering and physics than the vanilla functions that is just sine x or ln x or so on. Sure, they will occasionally show up here and there, but 95% of the time, it's going to be this. And this is where I always get straight with students. Guys, listen to this carefully. If you don't know chain rule, game over. Because you can't pretty much do 95% of the problems. You can't solve them if you don't know chain rule. So the last section of Calculus 1, 5.5, integration by use substitution, is backwards chain rule. Again, right? It will propagate through Calc 2, Calc 3 with partial derivatives. Again, utilizing chain rule. Calc 3 will have chain rules, which you're not going to learn one formula like we're going to learn now. You're actually going to learn a procedure that develops formulas, because every problem will have a different formula. So Calc 3 will have actually a shifting chain rule formula. You learn the procedure how to find the formula, and then you use formula to solve the problem. So it's going to be order of magnitude more complicated than what you see in this class. Over here, we are going to learn the chain rule in a very specific way. It will be contained to one formula, the derivative of the inside times the derivative of the right. So the derivative of the outside times the derivative of the inside. So that's in a nutshell what the chain rule does. The derivative of the outer function times the derivative of the inner function. And now we have to talk details and do 5,000 examples. What makes this crazy is that this synergizes with product rule, quotient rule. So you can have chain within a product, product within a chain, quotient and product in the chain, and so on. So it can be really crazy. And you have to have a good grasp on basic functions so you are able to distinguish whether it's a product rule or a chain rule, and so on. So to write the formula in, there are two ways we can understand this. The derivative of function composition is the derivative of the outer function times the derivative of the inner function. So this is the most standard formula that you can find. The detail. The detail here is observe f prime. What's in a parenthesis? G of x. So when you take the derivative of the outer function, you have to keep gx in it. And then times gx separate. So I'm going to explain that using sine x squared, because I believe that's one of the best functions to use to describe this formula, and then we'll have to just keep pounding on it. So here it is, sine x squared. So first, the most important part over here for all of you is to understand, clearly understand, that x squared is plugged into sine x. So there are two functions here. The outer function f of x is sine x, and the inner function g of x is x squared. How does the function composition works? You will say, if you want to compute, you know, when you want to compute, let's say f of pi, you would replace, right, since you replaced pi over there into x, you would put sine of pi, right? So what's the f of g of x? Well, it's clearly sine of g of x. So the function composition, now this is the pre-calculus part. So what's f of g? F of g would be sine of g of x, which is actually sine x squared. This is not multiplication between sine and x squared. Sine as a function has to have something as the argument. So you can't just say, oh, this is sine times x squared. Hell no. This is x squared replacing the original x that was there as the argument of sine. So now I have created the function. So I understand now that this is the out, this is the in part, right? The inner and outer parts. And the formula calls for the derivative of the outer function. Now what's the outer function? And what's its derivative? Cosine. But we have to keep g of x plugged in. So what is this equal to? Hold on. It's the derivative, hold on, the derivative of sine x is cosine x. The derivative of sine x squared is cosine x squared, okay? So you have to keep whatever g of x was there initially, you have to keep it. You are working on the outer shell. And then this whole thing will be multiplied by 2x, which is the derivative of the inner function, which is x squared. So the final answer is 2x cosine x squared. This part here is called the chain, right? It's the next link that follows. So we kind of ignored the fact that it was the sine of a function. And we did it like it wasn't. The derivative of sine x is cosine x. But because it wasn't x, it was x squared, we are obligated to put x squared. So next example. What is the derivative of e to the 10x? Now, what is the derivative of e to the x? E to the x. So what is the derivative of e to the 10x? E to the 10x. Times the derivative of 10x, which is 10. So the answer is 10e to the 10x.
Is that because when you separate them, you get 10x and e to the x?
Very good. So the decomposition here will be f is e to the x and g is 10x. And then that 10x plugs instead of the x to make a function composition. Getting green? Yeah, cool. I'm going to actually move this line. Let's see. How about the derivative of square root of x squared plus 1? First of all, you cannot take square root here. I've seen in 2 cases on the exam and I went, ugh. You can't take square root because of plus 1. All right, so again, what is the main function here? Square root of x. So square root of x is the boss. Cool. And what's plugged into it? X squared plus 1. Good. Now, we think first about the outer shell, which is the root x. What is the derivative of root x? 1 over 2 root x. Yes. So the derivative is 1 over 2 root x, but remember you have to keep g plugged in. You have to keep g plugged in. And then the derivative of the inside function, which is 2x plus 0, so it's just 2x. So the answer is 2 and 2 will cancel, x over the square root. I'm going to write this over here in blood. Keep the g plugged in. Keep the g plugged in at all times. All right, next example. What else do I have? The derivative of something interesting. How about e to the tangent x? Because we can. It's okay. We can put anything in. There's no application for this thing, but it's okay. Again, what's f? What's the outer function? E to the x. What's the inner function g? Tangent x. Very good. All right, so where do I begin? Yes, so the derivative of e to the x is e to the x, so I start with e to the tangent x. Good. And then times the derivative of tangent is? Very good. Secant squared x, yes. Of course. Ta-da! Swap them now. Function composition is not community. All right, so think of this one a little bit, and then, as Nike would say, just do it. What's the outer function? Tangent x is the outer. And what's the inner? E to the x. Awesome. So now, what do we have? Secant squared, as my pen dies over here. Yeah, I know, it's been time because it hasn't died all day. So, oh, look at that, 3 minutes left, and then another 25 after that. So we have secant squared e to the x. So you literally think of this as derivative secant squared. And then whatever is there, just copy it. Like Control C, Control V. All right, that's it. Because in the formula, right, this g here is exactly this g here. There we go. So in the formula, these two g's are exactly the same thing. That's why I am copying e to the x. And now, times the chain. What's the derivative of e to the x? A to the x. So the answer is e to the x, secant squared, e to the x. Can you factor out e to the x?
No.
Hell no. Exactly. The answer is hell no. Over here, f is tangent, and g is e to the x. So they swap the roles. All right, so since you did so well with this example, how about tangent of e to the 10x? What's going on now? Can anyone tell me?
Wouldn't you have to like make it add a third layer?
Nice! Add the third layer. Because f is tangent x, and then g is e to the x, and then h is 10x. You see, earlier it was e to the x. That was basic. But e to the 10x is not. So now we are adding the third layer. Very good. So now we have f is tangent x, g is e to the x, and h is 10x. Because look, you take this 10x and you plug it here, and you compile e to the 10x. And you take that e to the 10x and plug it there, and you compile tangent e to the 10x. So how many things, right? How many products are we going to have? 3, right? So what's the derivative of tangent? Secant squared, Control C, Control V. Good. Then, times, what's the derivative of e to the 10x? Aha. And then, times 10. We have to have 3 parts because we had 3 layers. Now, the biggest confusion is, how do you know how many layers should I have? Because technically every derivative could be 0, right? Because if you take derivative of 10, you get 0, multiply into everything, kill it, right? I know the number of layers because I am insanely good with function composition. When I look at this, I know there are 1, 2, 3. There they are. And I know 1, 2, 3. If I go the 4th one, that would be 0 and it would kill. I've seen exams like that, unfortunately, where students had for every chain rule 0 as the answer. Because keeps taking derivatives until it runs out of numbers, and obviously the last one will be 0. And that kills everything because it's multiplication. That's clearly wrong. Are there going to be some that will be 0? Sure. But 1, 2, 3 layers 1, 2, 3 creatures, done deal, right? So you have the derivative and two chains. Yes?
So an example would that be like if you gave us E to the 10, or if you gave us 10 to the E to the 10?
Yeah, very good. Right? All right, fine. Let's take a look. All right. So how about
This is spice one.
yeah, that's what I'm conceptualizing this. So cosine, well actually first let's do the vanilla and then the spice right after that. You've seen sine x squared, but you didn't really see sine squared x, right? So here's a cosine cubed x. What's the outer function here?
No. No. Cosine.
What's f, what's g?
What would be equal to cosine?
X cubed is outer.
Oh, it's good.
X cubed is outer, and cosine is plugged in. And for those of you that are going, what? This is the same as this. Learn your trig notation. So x cubed is the boss, right? Cosine is plugged in. So now it should be clear what the answer is. What is the derivative of x cubed? 3x squared. Now look at me, write 3x squared. Everyone, look at the screen. 3x squared. See that? And then times the derivative of the inside, which is negative sine x. So the whole thingy is negative 3 sine x cosine squared x. So meditate on this for some time. I need you to see this. Here, I'll use the eraser. I need you to see this as x cubed. You see it as x cubed? Eraser cubed. So what's the derivative of eraser cubed? It's 3 eraser squared. And I don't care what this represents, right? So when you rewrite it, guys, your ln cubed, people go crazy when they see ln cubed x. Same deal. The notation works the same. This cube cubes everything. This cube being on x or being here is a huge difference. You scroll up, right, well, in your notes, flip, and find the sine x squared. Much different example, much different outcome. So, again, eraser cubed is 3 eraser squared, and then the derivative here. Now, by Brian's request, spice. Good one. That's how awesome education is. I solved all the easy problems and then have fun. Next one is even going to be worse.
I'll make a way. 11.
Would the world peace be sufficient? I don't. Okay, thank you.
Too late now. What? 11, 12.
Oh yeah, it doesn't count. It's good, please.
Whatever. Nothing value honestly.
Then he wonders why he never received a scholarship for
I
for
know.
Rotaract. It's like running the mouth constantly and then dare to lift heavy, but fails to inspire others.
I inspire all of them.
The best line: "Why you joined Rotaract?" To find girlfriend. It's like, wow. No, it wasn't you, but
I think I said it because it looked good on a transcript.
join Rotaract. Yeah, it looks good on transcript. Great, excellent. Yeah.
On my scholarship form.
Did you fill for the scholarship? For
I'm
the?
not coming back here though. It was next year, right?
Oh yeah, that's the one. That's the only one.
Yeah.
But that's okay. There are gonna be another 3.
It's okay. I still wouldn't have gone there.
How do you know?
Personal bias.
Personal bias? Wow.
Yeah. I've made some enemies about that.
Okay. How many layers?
A group rating.
3 layers. What is the first layer? F. X to the 4th. How about G? Cosine X. And how about H? X to the 3rd. Now, plug it in, right? X cubed goes here, becomes cosine X cubed, and then that goes here, becomes cosine to the 4th. So this 4, you can put the parentheses and put the 4 there, right? Put the parentheses and 4 out there, and you see that's the boss, right? So, let's go. The derivative of x to the 4th, it is 4, and then we have eraser, right? So cosine x cubed, everything cubed. So that was Control C, Control V on cosine x cubed part. Now, what's the derivative of cosine? Negative sine x cubed. Nice. And then? 3x squared. Good. So now, overall, negative 12, 4 times 3. Negative 12 sine x cubed cosine cubed x cubed. You can put cosine first if you want to, but
Yeah, x squared.
what do you mean x squared isn't there? What do you mean x squared isn't there? It's, see it right there? X squared. You can't miss it. Here.
I need to get reading glasses.
Awesome. Well, you really can't see that. All right. Make me zoom in. Thank you. All right, so one more time. This is a spicy problem, okay? If it helps, put the 4 on the outside with a parenthesis. We see that x to the 4th, so everything is raised to the 4th power. Then we have cosine x layer in. Then we have the most inner layer, x cubed. So derivative of the outer, so that will be 4x cubed, negative sine x. You keep copying the guts, G, right? Guts. G stands for guts. And if you're vegetarian, this is really not going to go well for you. Okay. Ready? Yeah, you're ready. Look at this. Now we open the gates of hell, so now we just go along with it. All right. And then I leave before I get shot or something.
Is that sine x in the power or just regular?
That's sine squared x.
Okay, I wasn't sure if it was next to the 10x or not.
No.
10x squared sine.
Yeah, I wasn't sure if it was in the power, which would make this more annoying.
I just simplify it? Oh, you can't add them because this is not bigger. You can't do it up. You can't add that to that. Okay. So like, we have to change it like I'm back to that because it's like two spaces. And I put a sign. So I told them to use the only one to take into the two here. And I did easier plus
Outside of sine x squared. You're just separate. So we have to use product rule. So then take two separate problems. E times the x. That one first.
I know I told you that.
Algebra for that. Yeah, derivatives for that. Have our v derivative and our v regular. V regular is v times the x. V derivative ends up being n v times the x. And then this one wants u. So then we have regular u already. U derivative, which is
That's just 5 because we got the 5 sine. Yeah, 5 sine. That's plus. Yeah. I don't have to more simple out.
oh yeah, because it's two separate yeah, then product rule that one. And then chain rule both, and then product rule both rule. So they're not beside each other, so two separate problems, chain rule that, and chain rule that. And product rule both your respective results to get your actual result. And I think that's right that I want, but I will some.
Well, that's what I was saying, because I did discuss a lot about it. I had like, yeah, because and it's like, I don't know about you, but when I like to do the labs, I like to be chilling by, no, not
Yeah, the non-derivative form, which is down here, defined as u, which is sine x squared.
I need like really
Same thing as it up there. The derivative form, which I because it's not sine x is
because some people unironically listen to classics one. Does it work? Like, or is that just like? Yeah.
So what is the technique that we use? Product rule. Nice. Why? Because two separate functions here, two separate functions multiplied. So I will write that this is two chains in a product. And I'll put the red dot there, which might help. So this is f and g, and then each one of those breaks into two when you take their derivatives. E to the x 10x and x squared sine x. All right, so how do we do product rule? We copy the first, e to the 10x, times derivative of the second, well, that's 2 sine x times cosine x. Remember, it's x squared, so it's 2x, which is 2 sine, and derivative of sine is cosine. So that's the first, plus, so this was your f g prime, plus g f prime. So copy g is sine squared x, times f prime, which is derivative of e, is e, 10x, times 10. Now remember how I told you, get used to factoring everything you can now, because, you know, later is just hell. We can go in two routes in this problem. You can either factor out, which is better, 2 sine x, or you can keep 2 sine x cosine x as sine 2x. But you have a sine squared x and a second one solving equations that way, where you have 2x in one and x in the other one, is a living nightmare. So we are actually going to factor out 2e to the 10x sine x, and the only thing that it's left in the first term is cosine x. On the second one you have 5 sine squared x. No, 5 sine x, because one sine is out, factored out. So this would be the factored out solution. And you know what? Most of you are able to kind of grind through products and chains when you get sufficiently experienced with it. This trips you more than actually doing derivatives. So practice factoring, guys. Chapter 4, you do exactly the same thing, but now you have to go and say equal to 0 and solve for x, which is actually incredibly easy if you have it factored. Because now this is chapter 4 talk, and I'm going to erase this, but you have 2 equals 0, no solution. E to the 10x equals 0, no solution. Sine x equals 0, you see each factor is equal 0 independently. And that one has x is n pi, right? And in f is 0, it's 0, so infinitely many solutions. And then you have the only one that it's really bad is this one, cosine x plus 5 sine x equals 0, and then you actually have to unleash trig to solve that one. But for the most part, guys, you will have to factor this because chapter 4 will require to continue after the fact that you took the derivative. Chapter 3 is just teaching you how to take the derivative. And then chapter 4 is applications of derivatives. Word problems, spicy examples, linearization, all of the stuff that we actually use the derivative for to make money with is in chapter 4. So right now with you're doing yourself a favor and learning basics. All right, well, that's it for now. We'll continue with next one. We'll do more of these. Hopefully you guys will do homework, lots of it.